Now imagine a situation when you have two different samples from the same population. Let's say again we have a problem of estimating a weight, and we sample 100 people and we measure their weight and we calculate the average, and then we sample another group of 100 people and we calculate their weight and calculate the average. Do you think the averages will be the same? It's very unlikely that those averages will be the same, just because we have different groups of 100 people. And in fact, the average number or the average weight is itself a random variable. So if you think about this, if you go from one group of people to another group of people and you keep doing that, then every time you will observe a different average weight inside this group, and this average itself happens to be normally distributed random variable. And this is the fact that is called the central limit theorem. Central limit theorem, or CLT. So CLT, central limit theorem, tells us that the average is a normally distributed random variable with a mu and me, and variance s squared divided by n, where s squared is the estimated variance of from the sample. Okay, and another name for it, this standard deviation of the average is also called, so the standard deviation of the average is also called standard error, just because it measures the error in the estimates of the averages from one to another. Okay, so that's the fact, that's the central limit theorem, and this is some of the terminology on this slide. Now, once we know how to quantify the average, and that average is a random variable, now we can say something about confidence intervals. And you remember when we talked, so if we know that something, again, so that, let us write it down. The average estimate, so it will be a normal distribution itself. And now what would be our best guess for the mu, for the mean of this average? Well, it's gonna be x bar itself. So x bar is just the average calculated from the data, and again the variance is s squared divided by n. We take this fact and then we take a property of the normal distribution. Remember, we can say that 95% chance that a normal random variable is going to be between mu minus 2 sigmas and 2 plus 2 sigmas. So we put this fact, and now we can say that we have a confidence, it's called a confidence interval for the mean. So confidence interval for x bar, so that's the mean. So basically what we do here, we do a statistical analysis of the mean. Instead of taking a sample and calculating the average from the sample and claiming this is the true value of the average, we say, okay, we don't really know whether it's true value or not. There's some variation. Potentially, if we go from one sample to another sample, so there's a sampling error, for example. There are other sources of the errors, but mainly we are talking about here the sampling error. And we can quantify this deviation among estimated means by saying it actually follows normal distribution. We know the mean of this we don't know the mean, but we can estimate it from the sample and can estimate standard deviation. And now we use the property of the normal distribution to say with 95% probability the true mean is going to be inside this interval. So it means that with 95% probability, true mean, which we don't know, true mean is inside this interval. Okay, so this is central limit theorem combined with the property of the normal distribution allows us to calculate confidence interval for estimated average from the sample. And the related concept is what is called prediction interval. So prediction interval tells us so let's say I measured the weight of 100 people and I calculated the average. Now the question is, if I'm gonna go grab another person, just one person, and I'm gonna measure the weight of this person, what would likely be the weight of this person? Can I quantify what would be the 95% confidence interval for my next measurement, for my next observation? And so this interval is called the prediction interval, and of course this interval is going to be slightly wider than the confidence interval for the average, just because deviations in single observations in the weights of individual people is larger than deviations in the average, and the prediction interval answers the question what range of value are plausible for a single future observation. And if we want to find 1 minus, so basically for 95% confidence interval, we need to specify alpha to be 0.05. And the value for is the 95% prediction interval is x bar, so the average itself, plus minus, so this is the quantile of the normal distribution times s times the standard deviation of the sample. So far this is this is what we see in the confidence interval for the mean, and then you multiply by this additional factor here, 1 plus 1 over n and square root of that. So that's basically additional multiplicative term, and this number is going to be larger than 1 because we have 1 plus something under the square root, so the interval is going to be wider than the interval for the mean.